Today we have a guest speaker, Xavier from the University in Zurich, ETH Zurich, and for his master thesis, he worked on implementing a 1,000 brains system on process and memory chips. It's a really cool and exciting project, and yeah, happy to have you here, Xavier, to present it.
Thank you, thank you. I'm very anxious to present it in front of all you smart people, actually. But I'm also incredibly honored and excited because, I mean, you guys are literally the ones working on this. So I'm very excited, and I hope you somehow found some value in whatever I'm going to show you today.
I
Okay.
think we
This
should come.
plate- yeah, it's a beautiful coffee cup, and I thought I was so original when I picked it. But just to place a rough context, this work is basically about scaling 1,000 brains and seeing the impact of scaling 1,000 brains on computing systems. And basically, what we have 1,000 brains, it kind of looks like this. I mean, I really don't have to explain this to you, but I'm still going to do it. You basically, at every step, get a patch from the environment, and the model chooses potential to issue a motor command to move the patch in the environment. And what the models are composed of is these sensor learning modules and also a motor system. Now, the very interesting thing for us is that scaling of 1,000 brains happen through adding more and more learning modules in the system. And I think I've been looking at what you guys were doing for a long time, and I incredibly, let's say, convinced myself. Like I've always been like, okay, this is really cool. What you guys are doing, it's incredibly cool. Honestly, it's amazing. But I think one of the most convincing piece and which kind of served as a great motivation for this work is what you published in your systems paper recently, which is basically those graphs here, those let's say silly comparisons against vision transformers. But I think it was really important to show these quantitative advantage of Monty. And what it's really showing is these rapid, continuous, and compute efficient learning capabilities. So that's the first motivation that kind of grounds this work. Because I think when you have such amazing results, it really begs the question, okay, like these models sounds like they're going to be a big deal. Like what are the consequences on computing systems? The second thing is that, well, if you really do believe that these learning modules are modeled after cortical columns, you really wonder, well, why not scale these 1,000 brains to the size of the human neocortex? And what it would look like is basically 200,000 cortical columns kind of look like this. And more important, I mean, but beyond human neocortex, which is basically this guy here, you will also have like a cut cortex, let's say, like a smaller scale, like only 2,000 columns. You'd maybe have before that guinea pig scale cortex, 400. And now maybe I'm entering into a territory of, I'm saying stuff that is not exactly accurate, but I'm going to keep going, and maybe mice with 100 columns. And the question that we really want to answer here is, when you go up this table here, what's the consequences on computing systems? And basically, the first bit of answer that's given to us really is into this loop here, because this loop is basically what's called an autoregressive loop, which means that your responses at step t plus 1 really depends on what you compute at step t, and you cannot really do these multiple steps in parallel. And so if you want to parallelize anything, if you want to make it faster, you really have to do it within a step. You cannot really do it across steps. Luckily enough, in 1,000 brain systems, you have a huge number of learning modules that you would basically scale up to. And so this kind of gives you some kind of parallelization opportunity within a step. You can just parallelize across learning modules, basically. And so this is what we're doing here. We're trying to investigate the scalability of these 1,000 brain systems on GPUs, on CPUs, and on processing in memory. I'm going to explain what this is later. And the two things that we're going to look at is your beautiful code base, Monty, that was released not too long ago and continually improved, I guess, which is written in Python and built using explicit 3D graphs. And I am gonna do something a bit that I have no business doing, which is that I'm gonna jump. So the goal of this work was to also represent the computational demands of long-term thousand brain systems. And when you look at the Thousand Brains project, you talk about like the long-term goals. And you mentioned how in the long-term goals, you might want to incorporate elements of low-level neocortical processing, basically. And what I'm going to try to do is that what I try to do basically is that I kind of introduce a novel thousand brain systems, which basically is implemented using these HTM networks, those beautiful HTM networks that have been built, well, now for 10 years probably. And basically, yeah, it's to align with the long-term goals of the Thousand Brains project and really represent them well computationally. That's what I tried to do with Montyll. And I'm going to explain in further detail how it's actually implemented later, basically.
Do you mind if we ask questions as we go along, Xavier?
Of course, of course.
So, I mean, it's all great. Why did you feel you wanted to go back to the HTM stuff? Is that because it may fit better to the kind of hardware systems you're looking at? What was the motivation for that?
Yeah, that's a great like observation because it's exactly this. We had some kind of a hardware constraint that was really hard to satisfy with Monty itself. But the second thing is that if I Monty is just what's yeah, I kind of wanted to represent the long-term computation. I thought I could represent you know what I'm saying when I say this?
Well, yeah, I know, but it's an interesting choice to go back to the HTM stuff. Because a lot of that's not implemented explicitly in Monty. We have no neurons in Monty and things like that. But it
Mhm.
might be more suitable for certain processing elements. So I was just curious if that was the reason why. If that's the reason why, that's good. We can keep going on.
Yeah,
Yes, that
if
is
I
the reason why.
understood you right before, Xavier, I think the issue was that Monty deals with kind of continuous 3D space and a lot of precise floating point operations to calculate locations in that space. And on process and memory chips, you needed an implementation that could work with like 8-bit integer operations.
Exactly, yes.
Is that the okay?
You remember very right. That's exactly it. Um, but I was meaning to say something about this, which is that, well, that was the initial motivation, basically. And yeah, that was the initial motivation. Um, so let's first talk about GPUs, because I also seen that there's been a lot of discussion in the forums on GPUs and why don't we use GPUs for Monty and why don't we accelerate all of this? And really, what I'm going to talk about here is very simple. There's this thing called the operational intensity. I know we've got some very smart people who know about this in this meeting. But this is basically the number of operations that you do for every byte that you fetched. And what it measures is basically how much data do you reuse within your program. And basically, long story short, thousand brain systems, they have really low operational intensity. One of the big places where the operational intensity is very low within Monty, for example, is this KNN tree search. And just as a very rough aside, it reminds me of one of the effort that was going on maybe last year to do GPU-based acceleration of Monty. And I remember that it was a very smart person, and he like made all like he like hand built all these kernels for GPUs. But I remember he said he couldn't figure out the one that was responsible for KNN research. And as I understand correctly, that's the one that's literally responsible for maybe half of the computation time in Monty, or somewhere around this. It's a huge amount, it's a huge chunk of what Monty is doing. And he couldn't figure it out. And I think the reason why is just because this is basically the an- antithesis of what the GPU is good at. Like if you think about like KNN research is exactly what the GPU cannot do efficiently and fast, and also of course very hard to implement. And basically to make my point maybe a little more clear, this is the performance compared to the operational intensity. for typical like AI accelerators, like you have the NVIDIA A100 and the Google TPUs here. And basically what you see in this graph is that to the right side here, when the operational intensity is very high, this is where GPUs thrive. They have huge performance. And to the left, with the low operational intensity zone, this is where they kind of struggle. They have very low performance. And basically, when you look at deep learning, you see that almost over time, the models that are developed in deep learning like get higher and higher operational intensity with like basically LLMs peaking at a crazy amount of reuse. And so they're really good. These models are really good at using GPUs very efficiently. What we basically have in thousand brain systems is kind of the inverse because of this auto-regressive loop that I was talking about. And you're kind of stuck at very low operational intensities here. And GPUs basically suffer bad performance there. And so we deem it not to be a great fit to scale thousand brain systems. Now, I will say the following because I wouldn't say GPU is necessarily the enemy or that it's like never to be looked at again. After talking to like a lot of smart people in the like high performance scientific computing, what I understand is that GPUs can be used to make thousand brain systems like slightly faster maybe, but it's not gonna revolutionize like the speed of these. It's not gonna do the same. It cannot do the same thing that it did for deep learning systems. Basically, is my main point. So now you have CPUs, and the idea for CPUs is basically, well, you put like learning modules within different cores. And basically, really the question that we're asking ourselves in this particular setup is not necessarily how much computation is done within each step. It's actually how much data is fetched to generate motor commands. So at every step, you get a patch from the environment. Then you step into the sensor module, you step into the learning module, and you step into the motor system. And we really do wonder like how much data do you actually need to compute all these. So think maybe about like the explicit graphs. How much space are they taking in memory? All these object models that you're storing within the learning modules. And basically, if you want to scale to like 2,500 learning modules, like yeah, for Monty, you would have a data movement per step of maybe up to 100 gigabytes. And for Montyll, you would have the same kind of, in the same ballpark of 100 gigabytes per step, which is a good amount of data movement. And the question is like, can multi-core CPUs handle this data movement? And so when you think about multi-core CPUs, you really have this setup here. So you have the core, the logic basically that actually does the operations, and the memory, which is completely separate. And at every step, you need to fetch 100 gigabytes. So we assume that the memory, there's plenty of memory there to accommodate all the data we want. But there's these things called caches in CPUs, and basically it's not big enough, and we're kind of overwhelming the caches. So we do need to fetch all our data from main memory. And what saves us is that there's quite a large memory bandwidth, but also not even the memory bandwidth, but also really smart prefetchers, which means that we don't we can basically prefetch, like basically modern systems, they prefetch the data before you even need them, so that when you need them, it's exactly where you want them, where you want it. It kind of hides this memory latency. And so we can deem it as a good candidate to scale 1,000 brain systems. Now, the third option we had is processing memory stuff. And if on the left side you have this traditional computing paradigm, which is the Brunner model.
Xavier, before you go on, so what was your conclusion about CPUs? Did you say, hey, these systems could work up to a certain number of learning modules? I mean, 2,500 is that doable, and above that's not doable? What was the limit there that you kind of concluded?
The limit, I mean, do you want me to talk about it now, or can I talk about it later? Because I have it later.
About later. I just you were going on, so I didn't know if you're going to come back to it. So
yeah, maybe it's a bit confusing. So basically, this part of the presentation is basically the motivation.
Okay, all right, keep going.
So for this processing memory stuff, Um, it's basically it's a very old idea actually. It existed since the 70s. Computer architects have always asked themselves like, why does memory and logic need to be separate? Why can't we like basically put them together? That's this idea right here to the right, where you would basically have processing elements really, really near the DRAM cells. And the idea behind this is that, well, if at every step I need to like bring in 100 gigabytes of data per step, well, if you actually have processing amounts near the DRAM cells, you really only need to like bring a very little amount of data per step. And this is because you basically have this huge number of like what's called these DRAM banks. And you place some kind of a very small core very close to each of these DRAM banks. And what you can do if you do this is that you can literally compute the response of all these learning modules in parallel. You don't have to like each little core is responsible for one learning module. Whereas in the CPU, if you have like, for example, 30 cores and you try to put 2000 learning modules, where each core is responsible for like, I don't know, like 100 learning modules or something.
Just to check
And
my understanding, sorry, the architecture, if you, sorry, go back one more slide. So on the right here, the shared cache with the cores at the top, when would that component be invoked? Is that like
uh,
a kind of backup CPU for certain computations or?
their shared cache is basically used, it's used, so when you need to bring data from memory, from memory to the processor, usually it's very costly. Like there's a huge amount of latency involved. And so what uh, the architects of the people building processors like Intel have been doing for the past 50 years is that they've been saying like, okay, I don't need to bring data from memory every time. Maybe I can build a very small structure called a cache and
Right, no,
put,
sorry, I more mean, so the processing in memory,
yeah.
with that architecture, so you have a lot of the computation happening on the core associated with each DRAM cell, but then you're also showing at the top of this diagram,
Mhm.
you have a component with shared cache, the lower level or higher level cache, and then the cores up there. I guess I'm just
Mhm.
wondering, when does that tend to get invoked? Is that?
Oh, that doesn't get invoked. Yeah, that was yeah, that doesn't get invoked.
So
I see.
I
So
was,
so in the PI in the processing in memory, that just doesn't exist.
Basically, it does exist in the sense that you can have a system, like in practice, you have a system with a CPU, like a normal
That you
CPU,
could
and
use for some, yeah, if like a CPU is particularly good for something, then you could use it. But okay, I just wanted to check that wasn't like part of the processing and memory architecture.
yeah, I was
yes, yes,
confused by that too, because it says, okay, there's a core in the DRAMs, that's your thing. But then what's the thing on top? But you're basically saying you got memory someplace else, you have to feed it to the PIMs.
Or that
right,
like most computers would have a CPU as well
Right,
that can be
right,
used if you
right,
wanted it.
right.
Okay, thanks.
exactly.
Got it. Thank you for asking.
Yeah, yeah, yeah. That's exactly the a good point, which is like, yeah, it's there's gonna be a CPU there. Maybe in the future, like in 10 years or 20 years or something like this, people will just like let go of the CPU, but today it's gonna stay. So that's a good point. Um, So yeah, I think I was done. There was so the yeah, the very basic idea is that you would like basically compute all the responses and all the learning like activation roles that you would need in all the learning modules all at once, basically. And you can really scale to like 2,500 learning modules there because that's basically around the number of cores that you would have in these processing and memory um, architectures.
You say that based on existing chips, or is this some theoretical limit? I
Existing
mean,
chips.
okay. And are these production things or are these research sort of chips?
Production, it's I say production, but it's misleading production because it's production. It was produced in like 2019 and 2021. It's not produced today.
Okay. Yeah, because this has always been a field of research, the integrating memory and logic, but I wasn't aware of actually commercial systems that did this. Um,
Mhm.
so, but I wasn't even aware that they built any kind of number. I mean, that's been in research labs type of stuff. So, so anyway, you're saying that that people have done this. We've got some data on it. You're basing this on that. Because when you say, oh, you can do 2500, well, that's assuming certain things about certain decisions about the chips. And you're basing on that work that was done earlier. Is that correct?
Yeah, yeah. This is for a real world architecture with real world data, basically.
And so if there were commercial use cases, would it be possible to build processing memory systems with more than 2500 cores?
What do you mean modern 2000? Well, I didn't get that actually.
With more than 2500 cores. So
Yes,
building,
that's a good point. Yes, yes, yes.
could you scale it more, or is that kind of a technical limit for some reason?
Oh no, it's you can scale it more. It's a good point you're making because it really like it makes me think of like how much like if basically my point being if thousand brain systems become really as big of a deal as I think they will, um, like you basically could have a situation where the NVIDIA of processing in memory comes in and say like all these constraints, we don't care. We just want to tailor our chips to thousand brain systems, just like NVIDIA has made their GPUs really good for deep learning. And then you wouldn't have all these constraints of like only 2,500 of these chips, and you would have different architectures. Like the world is open there. Like nothing has been explored. There's a lot to explore in these chips architecture.
Do you have a photo by any chance, or I don't know if you? I'm just
Yeah,
curious, like how are they all wired up? Um,
like the actual system kind of looks.
and so how many of those DRAM logic cores would be on that?
That's 2,500.
So
Okay, I see.
is
So
this
so
from like a, go ahead. No, sorry.
oh yeah, sorry. So yeah, one of those PIM enabled memory cards is 2,500. Okay, thanks.
Yeah, no, the whole system here, the whole thing, the whole
Oh,
picture,
the
the
whole
whole
Okay.
thing.
thing. I see. Okay.
Yeah. So where was this work done? Is this done at ETH Zurich or is it someplace else or?
So yeah, the like some of the most seminal work on this, like okay, building the chips, that's a private company in France.
Okay.
They got acquired by Qualcomm not too long ago, and they kind of basically they're still doing great stuff, but they're put all their energy into LLM inference. Yeah, as you might imagine. So they
Right.
kind of let go of these other architectures that I thought were really good, and now the work of doing actual research on these chips that was done a lot at the Safari Research Group at ETH,
Mhm.
which is a research group that looks at memory and processing memory
I
and
think
stuff like that.
I wasn't aware that this work had progressed this far. It's interesting.
Yeah,
Um,
yeah, yeah. I'll have to say something to you actually at the end of the presentation. Um, yeah, let me go back to this thing. But yeah, actually, I mean, since you mentioned it, there's actually a lot of work from Samsung and SK Hynix, which are like the major DRAM manufacturers. It's all motivated by LLM inference. Uh, basically they have a huge challenge in LLM inference, which kind of warrants the use of processing in memory. It's actually it was actually like one of my like in LLM inference you have the same problem that we have here, which is this autoregressive loop thing. And basically, yeah, you can use like processing in memory to like make LLM faster at inference time.
Clever title.
What?
Have the clever title.
Was
PIM
it?
is
I
all
don't.
PIM is all you need.
Oh yeah, 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 yeah. Yeah. But yeah, I wanted to also give a little side note to data centers because in this work I really focused on single node system, which means like just a single machine. But when you think about scaling to massive amounts of learning modules, it begs the question, well, why don't you just use data centers? And I think there's a huge potential to use data centers, especially if your environments are virtualized and are not really the bottleneck. But one of the reasons why we're also like really looking at single node performance is because, well, when you really look back at how like these thousand brain systems, you really have this sensory motor loop with the environment. And while this might work for certain virtualized environments, if this is real world learning we're talking about, then having your model, having your scaling strategy rely on data centers is going to be a bit of a problem in terms of latency, basically. So we actually finally come to the actual well, this 1,000 brain systems that I'm doing, and yeah, really the main difference is basically on the implementation of these learning modules. And what I've tried to do is basically well, make them very close to the cortical columns, and especially to the works, the beautiful works that you guys have been putting out for quite a while now. So I have these three layers basically, like feature layer, location layer, and output layer. And the way that they're built is using these HTM networks. And we'll talk about like the hardware constraints that led to the motivation for these HTM networks a little later. And what we do basically in this work is that we look at all these amazing works that were done before, and we kind of like put it inside a signal network here. And we also make changes to the location layer. I don't know if you remember, you gave some kind of a presentation on your latest finding, Jeff Hawkins. I think you gave some kind of a presentation on your latest findings on location layer. And I also like took a bunch of notes from this to design the location layer in the way you described there, with this mini column structure basically, instead of having these modules. And yeah, so we provide some kind of, yes, sorry, go ahead.
No, I just no, that's a very deep topic, and so let's
Deep
not go there
topic,
right
yeah.
now.
Oh,
Let's not do that
that's unfortunate because it's a very interesting topic.
right.
Yeah. So yeah, we do provide some like I don't know if the word I was gonna say unified mathematical description. I don't know if that's the word. I just basically like heavily take on all the mathematical descriptions that you have and yeah, try to unify it within a single description. And I guess you kind of have to look at the paper for this because I'm not gonna talk about all this now.
So just
And
to check, what could the system then actually perform inference, or was it more to have all this kind of codified so that you could kind of at least simulate what the number of computations probably would be?
good point, simulate.
Okay, yeah. So it wasn't like there was synthetic objects that you were learning and performing inference with or anything.
Yeah, yes, you do, but basically the system I've built, unlike your beautiful system, which is useful for 3D object recognition, my system is useless so far. Uh,
Okay, but like, and that's fine. Like for I think the research question you were exploring, I just wanted to understand because like for example, some of the HTM papers used like synthetic objects which are like a sequence of SDRs, and I wasn't sure if the system was end to end enough that you could actually learn and do inference with like SDR based objects, or if it was more just like these are the computations that should be happening, and so this is approximately what the like flops or whatever would be involved.
I mean, sort of both are true, because I am in the end really doing computation on these like synthetic SDRs.
Oh, okay. Yeah.
It's just that they don't. I'm not even looking at if it actually learns or if it's actually useful or anything like this.
Okay. Yeah.
That would be a next steps kind of
And by
thing.
the way, I mean, I think that's the right thing to do at this point in time.
Right.
You're getting at a very, very interesting question that I've thought about for decades in some sense about, how much can you scale up our systems or these kind of systems using CPUs? What's the limit of that? And then beyond that, what is the next architecture? And what are its problems? So I think that if you can get to the answer to those questions without actually having them build a useful system, that's fine. It's a key question you're getting at. It's very interesting.
Oh, thank you, thank you. I do think there's a bit of importance to actually ground the systems because I could think that I'm representing the computational well, and actually I'm doing some stuff that is ungrounded, and the
Right,
real system would be different, you know?
right. That's the risk.
That's weird.
And so you're trying to maybe do a little bit of both, but right. I mean, yeah, that's the risk. That's why your work is challenging.
Yeah. Yeah. Um, so yeah. So we write this basically implementation of Montyll in C, and it kind of serves as the backbones of both our CPU and processing memory implementation. And now I'm basically only going to talk about this processing in memory implementation. And the reason why is because the design decisions that were made are best understood under the light of the challenges that we faced by like on the processing in-memory implementation. So if we kind of go back to the processing in memory stuff, so there's this is the promise of processing in memory right here. The promise of processing in memory is computing the learning roles and the motor commands, everything from all the learning modules at once in parallel. This is really important, a really important point I want to make, because we have a huge problem. Like there's a huge, like the type of parallelism, we always talk about how GPU does parallelism. And so people say like, well, the GPU is a parallel architecture. It can do things in parallel. And here we're kind of faced with this challenge of being like, well, we have these systems and we just kind of want to compute all these learning modules in parallel, but it seems to like not really be a great match. And the reason why is because the GPU takes its parallelism from aggressive input reuse, which is called batching. And so you have these huge batches, and this is how they achieve great parallelism. And in this case, you don't have this because when you think about thousand brain systems, it's a bunch of learning modules which are literally all different. That's the point of the learning modules, is to be different. And so you cannot reuse the weights across inputs. You literally have heterogeneous weights on heterogeneous inputs, and you somehow have to parallelize that computation. And the promise of processing memory is that you could, in a way, do all these computations in parallel. But what's the catch, right? If this sounds so great, there must be some catch. And there's a huge catch actually, which is that these cores, when you actually use memory manufacturing processes to manufacture logic elements, you suffer two consequences. One is very slow logic. So you have a frequency of 400 megahertz. That's like 5 times less, maybe 6 times less, maybe 7 times less than modern multi-core CPUs. And you also have, well, you also have within a chip your bandwidth to your actual bank. It's great, but it's not that great, basically.
Can I answer a question about that, Xavier? Why is the logic frequency low? I mean, it's not obvious to me why that would be.
Yeah. That's basically the reason why the logic frequency is low. It's not necessarily it's a consequence of using existing process. Okay, I'm going to start over here.
I mean, you could tell me
it's like an economic problem rather than like a fundamental physical problem of the universe.
Yes. What you said, yes, exactly.
Okay, so if there were economic incentives to work on these logic memory units,
right.
Okay.
Right. Okay, that's what I was thinking, because sometimes these things done early on, they use older fab facilities, and they use different design parameters, and you could so you're basically, what Niels has said is that you could improve this if there was an economic incentive to do so.
Yes, I think he's right. From my understanding,
Okay.
I see no reason why it's the case, but the economics doesn't
Okay.
work.
Well, that's important to know.
Yeah, I could talk about the exact technical reasons why the logic frequency is lower, but I don't think I'm going to bore you with that.
No, it's because it's not a limit of the universe. It's a limit of what they built so far.
Exactly. Yes.
Okay.
So this is these processing in memory chips. So the UpMem is the company. And well, I still have this very confusing stuff of having the CPU here and the processing memory system. But basically, what you have to the right is is what each core looks like. And each core is basically, there's this pipeline thing, which is basically a core. And there's this MRAM thing, which is basically the memory that you have access to within each core. And in between, you have sort of the equivalence of a cache, basically. This is because you don't access the data directly. And what I kind of want to highlight here is that not only, I talked about constraints in the last slide, there's more constraints actually to come. So these cores are very simple. For the same reasons that the logic is slow, or for other reasons, you can only do 32-bit integer arithmetic. And that's very interesting in, Yeah, you can only do 32-bit integer. You can only do 8-bit integer multiplication. And you kind of have to explicitly transfer all your memory accesses from this bigger MRAM to this cache thing. And these are some, yeah, big constraints basically. And
The
this kind of
explicit constraint, what is that in contrast to? Is that in contrast to the prefetching you were talking about earlier, or?
almost, you know, when you're programming on a normal CPU, you never care how and why and how your memory access, what actually happens when you request memory. Like, imagine you have some kind of a a variable in Python, like a equals 1, and then you read your value a. The system does it for you. Whether a is in storage, it's in main memory, it's in cache, you don't even have to care about it. The system actually does the transfer for you. For us, it's different. You have to actually manually say like, okay, this memory, this piece of memory that I want to access, I have to manually take it in and know and manage everything myself.
Yeah, okay, thanks. That sounds like fun.
That sounds like great. That was great fun.
It sounds like something from like, 40 years ago is what it sounds like.
Exactly. Yeah, it really is. It really
Am I
is.
understanding correctly, basically, that there's not a hardware circuit that does it for you, but it is essentially a software, makes it a software problem instead of a hardware problem, right?
Right.
And I can imagine in the future we can offload some of the software into hardware. Okay,
That's possible.
cool.
That's possible.
That sounds right.
Um, Now this goes back to the why I chose to re-implement in HTM, because it's actually a really almost like an enormous coincidence that it's very weird actually. When you really look at all the activation and learning rules you have in HTM networks, you really find a lot of the things that yeah, basically they really play well into the constraints of the processing and memory chips, like integer arithmetic, no need for super precise multiplication. You know, like the memory accesses, you can like kind of frame them to be very regular, and so it kind of fits well with this explicit, explicit data movement that you need. And so this kind of motivated when I first looked at processing memory, I really wanted to like basically port Monty to like integer and in C. And when I tried to do it, it felt really hard. It felt really, really hard. Like almost like, well, I don't know how to do this basically. And when I looked at like, okay, well, what if it was implemented in HTM networks? Well, it was still really hard, partly because I'm not that smart, but also it was not as hard because yeah, all the rules really play well into the limitations. And so yeah, one of the optimizations that we need to do here, maybe this part, I'm not sure if I want to bore you with this part, but this kind of enters in all the optimizations that we do to kind of make it work in our chips. The first thing is that we say that the activation and predictions, we kind of try to like, we're trying to keep it in WRAM. And this WRAM basically is a single like a single cycle latency structure, which means that whatever you have there, you can access in one cycle. So that's great. But as you can see, it's very small also. So you need to really make sure that whatever you have here is extremely important, because if you have stuff there that doesn't belong, you're losing space to other stuff that might be more interesting. So we try to really fit these activation predictions within there. And the way we do so is that we like basically pack all these into 32-bit integers, and we access them through bit serial computation. So we pay some sort of small computational cost. The second thing is fitting all these connections, the feed-forward contextual connections within this bigger bank, basically. And that's, well, the same kind of reason, right? If your connections don't fit in, then your learning modules doesn't fit in. You have to actually like use multiple of these processing memory cores for a single learning module. And so what we do here is that we basically use a compressed sparse representation, and we like kind of we managed to pack each entry, which kind of codes for which incident cell this connection is responsible for, and how like the permanence value basically going to pack it into a 32-bit structure. So that was the funniest part actually of this project here, because I've talked about how the limitations really play well, like how the rules of HTM really play well into the limitations of processing memory chips. Well, except for this one, I guess, because the boosting is well, as you can see, kind of uses basically rules that are like floating point and all that, and so we kind of have to do a bunch of work to like make it work on our architecture, which was okay, actually. It was doable. And this goes back to like, yeah, the explicit transfer. And I'm talking about here how I do the transfer, which is not that interesting, but basically it's kind of the way we do it is that we have, yeah, to the right side here is whatever fits into MRAM, like basically all our connections. And to the left here is the states and the buffer we use to actually bring in the connection, you know, because if you bring in the connection, you need some space to actually put the connections. And this is where they actually go in these things called private buffers. Now there's actually it's never ending, because there's another constraint of these chips, which is that there's something called fine-grained multi-threaded, which means that basically these cores never issue. Well, this is a very an interesting detail, but basically you need to parallelize the work within each learning module for the performance to be any good. And so the way we do it is actually very simple, it turns out, because you can kind of like take a couple of mini columns and map whatever computation you need to do within a mini column to a different tasklet, which is like basically a thread. So it's a different level of parallelism within a core that happens. And then the last step we need to do is that, you know, you have all these location, feature, and output layers, many operations that happen within a layer, and you kind of need to synchronize and have a bunch of barriers, because you don't want certain threads to work on states to assume that this, you know, you gotta have a, you know, like for example, to compute the prediction in the feature layer, you need to make sure that the activation in the location layer are done, right? Like everyone is done computing this. And so now we're actually getting to the results that we have. So this is gonna talk about also the, you know, how much I can scale and the number of learning modules and all that you wanted to know. So the methodology, again, I don't really want to bore you with it, but basically I use two CPU systems, one that has more cores, one that has less cores, and I use this processing memory system. And for the processing memory system, I basically use a cycle accurate simulator, which means that it's calibrated on this real world processing memory chips. And the reason why is, I mean, I'm going to spare you the reasons, but basically the numbers here should be trustable, basically. And we also test our implementation on something called a functional simulator. And yeah, the results that we have is basically that we successfully scaled this Montyll to 2,500 learning modules on both this high-end CPU and this processing memory systems. And that's about, in aggregate, that's about 45 million neurons and 16 billion synapses.
Xavier, is that on the CPU? Is that the larger one? The one with more cores?
The larger one, yes.
And yeah, how many cores is that? I forgot.
It's 48 cores.
48 cores. All right. I mean,
And
what are modern CPUs these days? They have a lot more than that, right?
it really depends on what class of CPU you have, but you're right. They can have a lot more.
Okay.
I
All right.
believe,
So with 48 cores, you were able to scale to 2,500 learning modules.
yeah.
Okay.
Like I think the key takeaway for you guys here is basically that CPUs are definitely like good enough. In the sense that, especially on the short and medium term, when you talk, especially if you look at CPUs that have a huge amount of bandwidth to memory, many cores, they're really great, actually. They can really scale to a lot of learning modules. And they can do so at sort of okay speeds, like number of steps per second that they can actually do. This kind of brings us to the results here that I have.
I'm saying on the previous slide, you're under the process of memory, you didn't have the equivalent of learning modules, but you did in terms of neurons and synapses, but I don't know how to translate those two. Is there an
Oh,
equivalent?
no, the processing memory also has a learning module.
I know, but what does it scale to the number of learning models? And
Yes.
PiM. So both of those,
Yeah, yeah, yeah.
both those systems can scale to 2500.
Yeah, yeah, that's right.
Okay, I missed that. Sorry.
Yeah.
Yeah. Okay.
Yeah, this kind of goes through the results here, which is this graph is the runtime per step, like how much time it takes per step in Thousand Brain systems compared to the number of learning modules. And what you see here is that for the CPUs, it kind of does exactly what you would expect the CPUs to do, which is as you increase the number of learning modules, it kind of just increases linearly the amount of time that you need per step because you're literally increasing the amount of work that the CPU has to do at every step. And for this processing memory implementation, where you don't have this because, as I said, they can just do all this in parallel. And it kind of results at the end of the day in like it basically outperforms the high-end CPU by around 2x for about 2.5 steps a second compared to 1.1 step a second.
And why does the CPU with more cores have longer runtime per step in general than the one with less cores?
The one with less core is basically has really good performance when it comes to like each core is really much more powerful, is what I meant to say.
Oh, okay. So they differ in more factors than the number of cores.
That's
Okay.
right. That's right.
And then the CPU two, the kind of fact that it sort of plateaus and seems to almost scale well as you increase the number of learning modules. What's that for?
That's a great catch. That's a great catch. I was going to talk about this right here. And so this has to do with, this is what you meant, right?
Yeah.
This has to do with this thing called instruction per cycle. And it turns out that it's really actually really unexpected. Really didn't expect to have this result here. As you increase the number of learning modules, for some reason, there's some kind of a sublinear scaling. It's because it's somehow you get a better instruction per cycle, which is as you increase the work, At some point, the CPUs are better able to utilize their cores because you give them so much work to do that they can just schedule instructions all the time, if that makes sense. Instead of
Interesting.
having to.
Do you think it would follow like a weird pattern where eventually that doesn't is no longer sublinear and then it starts becoming linear again, or?
Yeah, 100%, yeah. Because there's only
Uh,
like very tight amount of instruction per cycle you can actually issue.
Could you just remind me what you're talking about here? Are you talking about why this blue curve levels out at the top
Yeah,
there? Is that what you?
because that almost makes it look like, let's say we wanted 100,000 columns, that a CPU would be very close to the performance of the PIM. But I'm guessing that eventually it would also start to climb again, whereas
Yeah,
the PIM, which is truly parallel, will show this like flat.
yeah, that's right.
Uh,
That's right. Yeah.
Yeah, well, it's interesting because it's not obvious in this. It looks like it's plateauing, but you're saying it
Yeah.
probably won't. You're saying it's a
or
temporary plateau?
it's like just part of this function looks like that, but if we extrapolate it out,
It will go up
'cause
again.
it seems to be like a sweet spot. It sounds like you're saying like around 2,500
Yeah,
columns is like a sweet spot for making the best use of the cores.
that's right. Yeah.
This is also a log scale, right? So it could be
Yeah,
still
over
linear
3 months.
increasing.
I'm 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 sorry. Can you just? I want to make sure I get this. This is a critical item here. So
Mhm.
again, if I would extrapolate out more than 2,500 cores, are you
Yeah.
saying that the CPU two would get better than 2.2x, or would get less than 2.2x, or would stay at 2.2x? I'm confused.
It would probably get how to. So you see that I can't say exactly about the 2.2x, but I will say this: the CPU2 is scaling linearly, right?
Yeah,
We're and
up
then
to a
it's
point.
up to a point, and then it scales sublinearly.
Yeah.
you see these numbers like 0.76, 1.05, 1.87.
Yeah.
That's like for each of these for example, for 2,500 learning modules, there's about 1.87 instruction per cycle. That number cannot go higher than 2 to maybe 4. And so here you see this sublinear scaling because you can actually schedule more instruction per cycle. But after if you extrapolate, if you go to like for example, like 5,000 learning module or maybe 10,000 learning module, you kind of hit a point where the instructions per cycle cannot get more efficient. And so you get linear scaling again. Do you know what I mean?
Okay. Yeah, but linear, but at a lower slope than earlier here, I assume. Or maybe not.
Exactly the
No.
slope of here, yeah.
So I guess
Sorry,
the
yeah,
bottom line,
like maybe something like that.
it's not. I mean, all the words made sense, but it's still not clear why we would have this shape. But let me just the critical question is, what do we want to do? 200,000 learning modules. The PiM is. I can see its performance is it's pretty flat. It's going down a little bit, it looks like, but it's pretty flat. And the question would these, would the CPU architecture get better than 2.2? It sounds like it would. It sounds like over time the CPU would outperform the
No,
PIM.
it gets worse
Oh,
because you want lower. You want lower on here. So at that endpoint, 2,500, PiM is
run.
it's
Oh, right. It's
2.2
runtime.
times
It's
faster.
runtime percent. Oh, right. I'm sorry. I flipped around. You're right. I got it wrong. It's runtime per step. So, all right. So the transition point here is around, I don't know, several hundred, 400, something like that, or whatever that
And
is.
yeah, and then I mean, feel free to correct me, Xavier, if I say anything wrong, but like it sounds like as you extrapolate out, you're not going to get that's not going to be fixed at 2.2x. CPU is going to
Exactly.
start getting worse, and in fact, it's going to start getting worse at that kind of more linear
Right.
trend again. And the
So,
yeah.
yeah.
So basically, PIM for any large system, according to this, would be the better approach.
Right. So the key item for us is how far can we go with CPUs? Because the PIM architecture is going to be, a major effort, and
that's gonna be
and people are only going to do that when they see the commercial benefit of it.
That's
So
right.
we have to make commercially valuable systems with today's hardware, which would be CPUs in this case. And so it sounds like we can go. Well, there's no answer to this question, but the crossover here is somewhere around 300 and so learning modules, but still at 2,500 learning modules, you can do useful stuff with CPUs.
That's
Um,
right.
but the further out you go, the commercial value of using the PIM is going to get greater and greater.
Yeah, that's right.
That's a really interesting chart.
That was great. That's well summarized.
I've wondered about this for like decades. So here's the
Really?
answer. Yeah. Well, because
Very interesting.
I used to give every year. I used to give a keynote talk at the neuromorphic computing conferences they have. It was a big one, and I saw all these people trying to do all these new architectures that were designed just for neural networks and various types of things, and they just kept looking at it and like these architectures are really interesting, but until you know basically until you know what's on this chart, you don't really know when they're going to become important. And so I've always felt and I've hoped that we could scale. I know we could scale 1,000 brain systems, Monty, up to some number. I don't know what that number was, but I felt we could always build commercially valuable systems using CPUs, but you'd run into a limit at some point in time. And what is that limit? It was always an interesting question. And I never had an answer to that question, at least not as concise as this one looks like. I mean, this isn't a precise number, but it gives you a very clear indication of the nature of these things. We could do, even just doing a couple thousand learning modules would be a pretty damn interesting system.
Yeah.
So it's, but if you want to really create really impressive system, people, there's no reason people weren't going to scale this up, a factor of 10 or 100,000 more.
Yeah.
So interesting. It's very
That's
interesting.
why I think it's super interesting too. I think the first 1,000 brain systems are going to be scaled to like huge numbers, are going to be using data centers. I don't see why data centers, just standard CPU data centers, couldn't really scale up, especially
Well,
in
you brought up the reason why. It's the latency issue because my little hypothetical goal, which I think is real, but it sounds stupid, is okay, I want to have a bunch of robots on Mars that are building engineers and construction workers, right?
yeah,
And these are machines, and so there's no data centers up there. You know,
no data center up there.
the latency is minutes. But that just gives you this sort of understanding that when you come to robotic systems, real-time robotic systems, latency is a killer. And so, and now also connectivity is always isn't always guaranteed, and
Yeah,
so
I agree with
I
you
don't know.
100%.
It depends. It really depends where the thousand brain systems really, because first find their commercial footing. If it is in robotics in a factory, well then data centers could be fine. If it's robotics in the field, data centers may not be fine.
Yeah,
If it's vision systems in buildings and so on, well that's fine. You can use data centers for that. Um, but if I'm trying to manipulate physical hands and body to manipulate objects in the real world, robotic appendages like that, then the data centers may not work.
yeah. Can I show you something actually regarding this?
Yeah, it's great.
I'm gonna go ahead to this because I kind of wanted to talk about this. Kind of leads well into this discussion I wanted to have, which is I was kind of actually a little bit baffled when I learned about this. Maybe this is not going to baffle any one of you, but when you look at neurons and synapses in the brain, they're actually quite big. There's these biological like devices basically. They're quite small, but in a way they're quite big, especially when you compare that to the the manufacturing capabilities that we have today in like our most advanced chips, right? We're kind of building these devices that have like walls the size of an atom. Like it's really like you cannot maybe even get them smaller, like physically. And it's kind of what it looks like here, the state of the art of like the most dense thing the humans could ever produce. Our most advanced like manufacturing capabilities is this. This is like the most dense storage you could have in the world. And basically what you kind of find is that in the human neocortex, like you have 150 trillion connections. If you assume, maybe this is wrong to assume, but if you assume that each connection kind of encodes for maybe 8 bits of, permanence, 8 bits of strength, and maybe like 24 bits to like address, because neurons have an address space, you need to address which is the input, which is the output. If you assume 32 bits, that's 600 terabytes of capacity, right? That's pretty huge, especially for, the volume that it only takes. It's pretty small volume, right? It's like, yeah, it's pretty small volume. And, like the most advanced, most dense storage, like capabilities that we can have in the most advanced computing system, like you can max out everything to the max. It's only less than 30 terabytes today. And that would be huge. That would be a big system, a very power hungry system. And that's just for storage. This has no computation capabilities. So the brain can do computation within, it can do computation near the weights. Here, the NAND storage that would just be for putting things there, not even for computing with them. And so I don't know that
Yeah.
I thought that was baffling actually.
Well, is there a question there? Like,
There's not a question, but what I want to give, like the idea that I want to give here is that when you look at the human neocortex, which basically there's these constraints, 600 terabytes of footprint. It does some sort of macro level parallelism, right, at the level of cortical columns. Then it does some sort of mini column parallelism, right? There's like
yeah.
multiple columns which might be active in parallel. It kind of can issue multiple motor commands per second, and it kind of, the form factor kind of like fits within like a large coffee cup, basically. And that's basically like a type of density, like a combination of density and computing capabilities that just does not exist today. There is no like I don't
Yeah.
think there's a single technology that actually has a potential roadmap to have this.
Well, it's interesting because in Monty, there are no neurons in Monty. There's no synapses in Monty. But at the moment, there's no sparse distributed representations in Monty. Um, but there's a couple of reasons why. Maybe Vivian and Niels will be able to speak about this better than me because they built the system. But the we're trying to capture functionality of the cortex, but not necessarily model a brain. And it's very complex to do these things. It's much easier to do this with CPUs and typical memory architectures and types of operations that CPUs do. And so we've always debated: do we have to, where is that line between, what aspects of biology do we actually have to incorporate? Do we have to get the sparse distributed representations? Do we have to get down to, neurons and synapses and spiking? We don't think we have to. There's some line there. We haven't made that decision yet. We've chosen an architecture where we're going to see how far we can go before we have to change it. So yeah, if we had to model every synapse in the brain, I think we'd be in trouble. But we're assuming we don't have to do that.
Okay.
I don't know if Vivian and Niels or anyone else want to chime in on that question.
Yeah. What's your sense about all this?
Yeah. Yeah, I mean it's interesting. Yeah, and we I don't know if we ever released it, but yeah, we had like this discussion maybe a year and a half ago about kind of this neural roadmap, which is like, at what point would we consider bringing in kind of more biological elements? Like, what would be the threshold for it kind of
Well, I don't hear it anymore.
being a useful reason? Because full about it being such. Oh, sorry, maybe my connection was unstable.
I
Yeah,
was
no.
worried it was mine, but it wasn't mine because Xavier didn't hear it either. So yay.
Yeah, that there's some kind of advantages of having the system be less neural, things like interpretability and being able to visualize it and things like that. But it is funny because I think at the same time, although we're not doing it intentionally, there are more neural things I feel that have just naturally crept in because I think it's kind of inevitable, some of it. So like the way the evidence values accumulate in the kind of for the hypothesis nodes um, looks a lot like a membrane potential of a neuron fluctuating over time, until it reaches a spiking threshold. And we even have almost like a multi-compartmental concept now where some parts of that kind of membrane potential, if you will, change more quickly than others, and things like that. So we're not labeling them as neurons or anything like that, but it's interesting that yeah, like some of these kind of things will maybe come in inevitably, but whether that's things like SDRs and stuff like that is unknown at this point.
I think it's ironic in that today's deep learning networks are patently not biologically realistic at all, but they have neurons. And
Yeah.
Thousand Brain theory is very biologically is detailed, but has no neurons. So it's kind of a funny irony in that. But of course, we have
Yeah,
all this other structure.
it's maybe marketing because I've sometimes thought whether we should call our hypothesized nodes like EMA neurons or something like that, or it's like this
Well, yeah,
exponentially moving
we
average
can
and stuff.
think about that, but of course, most people don't. Most people understand that the important architectures you have to capture are macro scale and medium scale, and they don't have any of that. So, anyway, this is a very fascinating question. We all have to worry about these questions. I think you put it nicely here, Xavier, putting some numbers on it. But it's always been my assumption that we're not going to get to that level of detail. Where the level of detail we go to is not clear yet, and then what is the right computational architectures to do that? It's not clear yet. I think the whole idea of processing in memory as a concept, as opposed to this particular implementation you're working with, always seemed very promising because that's what brains are, right? There is no computing center and memory storage center. It's all integrated. So yeah, I think the encouraging thing is that we have a lot of runway here with what we're doing, and yet you're working on what happens when we run out of that runway, and which is going to happen. And so it's fantastic that you're thinking about it. Like, this is really wonderful work you're presenting here. So, like, because I'm not going to be able to think about this, and thank God you're thinking about it. Rami had to raise his hand.
Yeah, well, this is really interesting, really great presentation. I'm just wondering, could you talk more about are these PIM modules, are they doing any voting or are they talking to each other at all? Or are they like, each one is just running its own DRAM core thing?
That's a good question. I mean, in these current systems, basically, it goes back to what Niels was saying. These processing memory chips don't have it, so you have to do something like this. Actually, it doesn't really take so much time to actually take all the votes and putting back to all the chips, but they don't communicate via like actual physical links between them. You kind of have to bring all the data to CPU and then back to all the chips after aggregating.
I see. So there's a hub, which is like different from how I think we're thinking about the voting that happens between the layer 2, 3.
But
Exactly.
you're
It's
saying that's
similar.
computationally not a problem. It's a low demand.
As far
And I
as I
mean, it's
understand.
similar to how we do voting in Monty right now too. We first collect all the votes from the learning modules and then distribute them to the receiving learning modules in like the Monty class that manages them all. And yeah, as far as I understood you, Xavier, when we met before, it sounds like, well, generally the amount of information that's communicated between learning modules versus the amount of computations that happen within learning modules, is very small. So it sounds like that would still be doable to kind of collect votes and then send them back out to the process and memory chips.
Yeah, you
Or
put it
is
perfectly.
that a small limit?
Yeah, you put it perfectly. It's exactly right.
But how does it compare like the communication like bandwidth and speed or latency for these PIM modules who talk to each other versus like CPU cores? Do you think
So
that yeah?
if the processing memory chips could talk amongst themselves, um, you would have, yeah, you basically have a huge speed up on that specific step of communicating everything. Um, I don't exactly know the exact speed up numbers.
Yeah, no worries. Just wondering if you yeah, because a lot of the Thousand Brains, uh, a lot of it actually is about voting. So I think, to get the benefits, like to do real inference and get the benefits of this scaling, we'd have to consider at least some kind of local voting of like the nearest PIM modules.
Yeah,
Uh,
100%. I think, like this goes kind of back to what Jeff was saying about like there's a huge runway. Like, I think once people get convinced that thousand brain systems actually are a big deal, like I'm sure you'll have some kind of people which will basically be the Nvidia of thousand brains, and they will like build their chips like specifically like looking at all these design challenges of like, oh, voting, it's okay, local voting within all the learning modules. You need to pipeline parallelize across multiple levels of hierarchy. Like all the columns don't talk to each other, only a subset talk to each other. So how do you design the interconnects to go do that? I haven't I haven't talked to like looked at everything, but I can imagine this
Right.
will.
You would make a chip that's designed for this and would deal with all these issues. That's your future company, Xavier. You can start
That's
that
my
company.
future company. You believe
Yeah,
in me?
yeah, yeah. I believe in you.
I will,
You're
I'll make it
just
big.
you can do that if you want. If you want to, it's up to you.
Yeah. I
Um,
just a small $1 billion investment from you, Jeff.
what's most important is that we make the Thousand Brain series successful, and
True.
then people will want to put money into it.
Yeah,
Um,
that's right.
so, um,
You better make it very successful, please.
yeah, well, we're trying.
One thing
Hard.
I was just wondering is, yeah, so at the moment, Monty, the way we've implemented it, probably kind of for simplicity, is it's like a very synchronous system still, in the sense that like even if we have 1,000 learning modules, Monty kind of steps through all of them. It can step through them in parallel, but it kind of waits on all of them before it then kind of ticks through the next like sensory motor step. Um, but it may be in the future, particularly in like robotics applications and things like that, that you could imagine like a more asynchronous version where each learning module is truly kind of parallel and can just operate on its own cycle. But I was just wondering, yeah, in the current implementation, is there this notion of kind of a global kind of stepping function, and do you have a sense of like how much overhead does that introduce that like the fastest PIM module is waiting on the slowest one? Um,
Uh, yeah,
or
they
I guess
don't really.
in these simulations they probably all take the same amount because they're not actually yeah.
That's right. Yeah, they all take the same eyes. Like the computations are very regular
Yeah,
across the modules.
no, that makes sense.
No, but it's a good point. I mean, you don't have to activate every column at every step.
And with this hardware, could it support that? Could you like do you it sounded like you implemented the gates or what did you call them, the brakes that sync up all of them? Or no,
Yeah,
that was within
that was within.
so is there a explicit braking logic that you had to implement across the columns as well, or
Not really. I mean, the breaking logic is pretty simple. You just kind of wait for the columns to be done, and you kind of take
but
the.
so it's optional, it sounds like. Uh,
Uh, what do you mean optional?
as
So like
in you could run them, you could have all these different core memory units running asynchronously in this particular, what was it called, upmem. I'm just asking, like
Yeah,
in
yeah,
this particular chip, is that already a possibility?
that's already a possibility. Yes. Yeah.
Yeah, okay, thanks.
Let me related to this total 600 terabyte question. A lot of people are excited about emristors as a form of memory because it's so dense. Do you think that changes? That would be useful? Would that change anything? I've always been kind of skeptical, only because MRIS is a technology in search of a solution, and so I just wonder, because some people would argue, oh, the way you're going to get that density in memory is using emristors. I don't know if you have an opinion about that.
Yeah. Yeah. I believe, yeah, there's a lot of people who believe in, yeah, memristors, and I think they're really interesting. They do have this very like density promise that they could actually scale up to like better density than everything else. I'm skeptical on two grounds. Okay, so there's one thing that's really cool that's one thing that's really cool and kind of goes against what you were saying about, okay, so we might not want to like, simulate every synapse and every neuron. We might just be able to like kind of take a high level abstraction and kind of hide away all these details so that we don't have to have so much footprint. The one very, very important thing within memristors is that they have a lot of noise. So they can do computation, but they don't do computation like very like digital. They incur a lot of noise when they do computation, which means that you do need an underlying algorithm that can actually take in noise. That's kind of what
Mm.
HTM does. So, I have done very little like time thinking about this, but my idea is that, well, potentially, if you do have HTM networks, those SDRs, it could be robust to the noise that is incurred within memristors. So that could be interesting. Haven't seen anyone look at it yet.
Mm.
Um, so the second thing is that they have really bad write endurance, which is
Hmm.
that you actually change, in HTM networks, you change all the time, like the permanence values of all these synapses. And in memristors, if you have a problem where you can only write, like, for example, 500,000 times to a certain memory cell, then you're gonna have a problem soon, right? Because you're gonna run out of, your cells are literally gonna die.
Yeah.
Uh,
Well, flash memory has that same problem, and they figured out how to get
yeah,
around it by just
they
doing all
figure
this
out, yeah.
complicated mapping and so on. But I think those are good points, and I appreciate your opinion about them.
Yeah.
It's kind of
Uh,
I've kind of felt like, hey, maybe, I don't know, but as you point out, they require almost, if you're going to put them in, you can't substitute memristors for DRAM. It's like you have to change everything to make it work with memristors, which is a much bigger hurdle. Maybe that's something that happens, 40 years from now or something. I don't know.
Yeah. When's the first time you heard about memristors?
When?
Yeah,
Oh, a long time ago.
time ago.
I don't know. It seems like I've been hearing about them for 20, 30 years. I don't know.
Oh,
It
really?
was, yeah, it's like,
It's been here for a
yeah, I
while.
mean, the idea's been around for a long time. I mean, maybe people haven't implemented them until more recently. I don't know.
Yeah,
I don't
yeah.
know how. It was a long time ago. It wasn't a recent thing.
It sounds like you were giving like keynote presentations to neuromorphic chip people. So
Right.
what is
Well,
what is when you talk to them about it, what did they think?
um, let's see. When I talked to him about our work,
I don't know, like
yeah.
if
Well, first of all, I haven't done it in a few years. And so we've made a huge amount of progress since last time I did that. But I think, but we were talking. I definitely was talking about HTM type of networks and where we were going with all this stuff. I think what I had the impression was most of the people doing work in this field are academics,
Mhm.
and they have a thing that they're working on. They're trying to figure out where, what they can do with it. Not many people were sort of more broadly motivated, as perhaps you are, which is like, I don't really care about the particular technology. We're going to build these systems, and how do we build them? Not like, oh, I'm going to build MRistors, therefore, can you use my MRistors? I also think there's a lot of people out there who just have trouble understanding what we're doing. And I was just exchanging a message with Vivian about that yesterday. Um, you know, you get it. You're really educated about this stuff.
Thank you.
We're all excited about it, but for
Yeah.
some reason, it's hard for a lot of people to understand. I don't know why, but it's hard for a lot of people just to put it all together and say, "Oh crap, this is really important." So I would give these talks, and I'm not sure how, as many times as I tried, I'm not sure how many people I was able to penetrate to, some failure of my part to get them excited about these kind of things. I just point that out. We have a sort of a educational challenge we have to do. Um, I would hope most people would just like hear about our work and go, "Wow, that's exciting! I got to work on that." And most people are like, "Okay, whatever. Let me go back to what I'm doing," type of thing.
Yeah.
Uh,
You had I think
anyways,
you had an unreasonable effectiveness on me. I was like, oh my God, this is so
well, yeah, it's really, a famous scientist once said to me, it was a very, very famous scientist, and he said, "Does anyone else understand what you're doing?" I said, "Yeah, there's a few people." He goes, "Good, that's all you need, just a few people. But if you don't have that, you're in trouble." Um, so yeah, it's really a very really delightful that your level of knowledge and interest and understanding of this is it's very
thank you.
encouraging for me, a young
That
person
means a
like
lot.
you.
That means a lot to me. That's very nice to say.
So, I
Uh,
mean, I wasn't joking when I said you could create that NVIDIA equivalent. That wasn't
your,
a joke.
your compliment. Let's go. I'm so happy. No, it's
Yeah,
really funny
yeah.
actually because the reason why I first ran into your work was a couple of friends just didn't have a present for my birthday, so kind of run into the local bookstore. They got me your book. They thought like, oh, Xavier could maybe like this. And I got your book, and I thought like I looked at it, I was like, oh, what is this? What is this they
Was it
offered? What is, like it was the Thousand Braids book.
a thousand range book?
And I was like,
Yeah.
oh, what is this book? And I just couldn't put it aside. And then I read it. I was like, at the time, I was doing research in these processing memory architectures, and I remember that we really like it's a hugely promising technology where we literally it's useless for everything. Like there's no kill application. There's nothing that really makes it shine. And then when I read the book, I was like, oh, I cannot believe this. Like this is exactly like the right, like everything
I mean,
is correct there. That this is fit really well, and I was really happy about it. And
well, the
then
reason, yeah, go on.
yeah, I don't know. Like, yeah, I'm very mad at you because all the intense headaches that I've been having over the years are because of all of you who have made incredibly
Sorry.
interesting stuff for me to bang my head against.
Well, it is a challenging work, and one of the reasons I wrote the book is because you have to cast a very wide net because the percentage of people who will read it and really understand it deeply is small. And so you have to reach out to as many people as possible, and then you catch people like yourself who are brilliant and thoughtful. And no, I'm serious. It's pretty impressive. In a very short period of time too.
Yeah, that's really rush.
Wow.
Yeah, that's a cool coincidence. Your friend's getting the book for you while you were working on PiM.
No.
But yeah. Thanks again for this presentation and all this work. This is really, really awesome, and yeah, really nice
Yeah.
overview.
Yeah,
Appreciate
yeah,
it.
I've been super impressed the past months by like just the sheer amount of depth of all the past Numenta work, how much
That's
you
so
had to
cool.
understand
I'm very
and
happy.
implement, and yeah,
Headache.
plus
So,
understanding
lot of
process and
headache.
memory chips and knowing all of that side as well, which I have huge respect
guys
for
are-
from what I heard, how that works. So
Yeah. We had a couple
So-
meetings with Vivian. Yeah.
that's really great.